Hello, students. So, let's look at an example. I have a vector space V and a vector space W, and I have a basis for V, 1, 0, and 0, 1. It's a dimension 2 vector space. These are independent, and they form a basis. So, how do I make a linear map from V to W? Well, what that last theorem tells me is that I can pick any vectors I want in W. So I can let W1 just be, let's say, 1, 1, 1, 1, and I can let W2 be 1, 2, 3, 4. I know I'm picking whole numbers, not being very creative here. No pi or anything like that, or square root of 2. But let's see what happens here. What does the theorem say? Well, the theorem says that there is a unique map that sends V1 to W1 and V2 to W2. That is linear. So suppose I want to find out what is, so let's let T be the map defined by, and so this is just the definition we had in the last result, that T of alpha 1 V1 plus alpha 2 V2 is equal to alpha 1 W1 plus alpha 2 W2. Okay, so what does this mean? What are we doing here? Well, I didn't tell you what we're doing here, but I want to show you that this is a map that's defined on all of V and give an example of how we can figure out where things go. So say we have, I don't know, pick some numbers. You can't pick for me because this is a video, but let's say 2 minus 3 equals V. Then what's T of V? Well, T of V is going to be what? Well, first I have to write this in terms of our basis. So this is going to be the same as 2 times 1, 0, plus minus 3 times 0, 1. And then once I have this, I know where it sends this. It sends this to 2 times, well, where does 1, 0 get sent? 1, 1, 1, 1. And then plus minus 3, where does 0, 1 get sent? Well, it gets sent to 1, 2, 3, 4. So this goes to 2, 2, 2, 2, plus minus 3, minus 6, minus 9, minus 16. And this is equal to now minus 1, minus 4, minus 7, and minus 14. Because 2 plus negative 16, 2 plus negative 9, 2 plus negative 6, and 2 plus negative 3 are these 4 numbers. So that's an example, but of course I can do this for any V. Hopefully now you can see how this is always determined in a little case. Now there's one other theorem I'd like to prove. It's a short one. If T, I'll even abbreviate, I'll use this so I can use less words. If T is a linear map from V to W, I should say it's linear. Then T of 0 is 0. Now, first of all, understand what it means if I say T of 0 is 0. Where is this 0? Think about that for a moment. That 0 is the 0 in the vector space V. Where is this 0? Well, this 0 is the 0 in the vector space W, right? These are not necessarily the same dimension. They weren't the same dimension here, right? So these are different zeros. Like the 0 here would be 0, 0, 0, 0, and the 0 here would be 0, 0. Not the same 0, but this is still true. So how could we show something like this? Well, this is a nice little proof, but it's done in the text and in every text I've seen, so we might as well do it out. You might want to pause the video if you haven't seen this before and think about exactly how you might prove something like this. Why don't you take a moment to do that? Okay. So, proof. Well, I often say there's really only two tricks. There's really only one trick if you think about things in terms of the identity, right? I always say you can always add 0 and multiply by 1. Well, both of those are essentially the same thing. So what I'm going to do is I'm going to add 0. I know that t of 0, which is what I have here, I'm just starting with what I have, this is going to be equal to t of 0 plus 0. Okay, but t is linear. So since t is linear, this is t of 0 plus t of 0. So I know that t of 0 is equal to t of 0 plus t of 0. What could I do? I could just subtract t of 0 from both sides. Now, what do I mean, though, when I do that? I mean I'm adding the inverse of t of 0 in our abelian group, which is part of our vector space. So what is that going to give me? Well, I'm going to take t0 and the inverse of t0. So on the left, I have 0. But on the right, I'm going to have one fewer t0s. Associativity and all, don't have to worry about that. It's a vector space. So I get 0 equals t0, and lo and behold, I am already done. Boom. So that's a nice short proof. Now, if the map is linear, then t sends 0 to 0. However, if t sends 0 to 0, it is not necessarily linear. Don't go around thinking there are lots of maps that send 0 to 0 which are not linear. Now, we haven't done anything geometrically and talked about what a linear map might look like if we tried to graph it from, say, R to R or something like that. But you know plenty of maps that send 0 to 0 which do weird things, like probably sine x. Plug in some values for sine x. Even if this looks linear, because we don't have any idea, I mean, it doesn't look linear, but even if it looked linear to you, because we haven't looked at any physical examples yet, so we don't know what a linear map looks like, just try plugging in some numbers. Unless you plug in very extreme values, you're going to find that this does not meet the criterion for being linear. Okay, so one more time. If t is linear, it sends 0 to 0. But if t sends 0 to 0, it is not necessarily linear. Okay, let's find a way of combining maps in the next video, because that's one thing that we always do in math, right? If we have some type of maps, like if you define sort of continuous maps, and you say what happens if you combine continuous maps by adding two continuous maps? Is it continuous? Or when you define differentiable functions, well, what happens if you add two differentiable functions? Is it still differentiable? So the very next question that I'd want to ask here is, what happens if you add two linear maps? So we have two linear maps, both going from V to W. What happens if you add them? Is that going to be linear? So why don't you take a moment to think about that and meet me in the next video.